So let's suppose that someone claims to you, maybe the textbook or maybe myself, claims that 2 is an eigenvalue of this matrix. So I might ask you two questions. First of all, show that 2 is an eigenvalue. Of this matrix, A, which is 4, -2, -2, 4. So that's question number 1. And question number 2 would be to describe the eigenspace. Now, what's an eigenspace, by the way? How does it relate to our discussion of eigenvalues and eigenvectors? Right, it's the set of all, and when you say solutions, it's solutions to that eigenvalue eigenvector equation associated with this eigenvalue. So it's the set of all eigenvectors for our particular eigenvalue, lambda equals 2. So in other words, it's the set of all vectors x such that a times x is equal to what? Well, if the eigenvalue is 2, then when we're talking about the eigenspace for lambda equals 2, we're talking about the set of all vectors that A doubles. The set of all vectors that A has the effect of just multiplying those vectors by the scalar 2. So first, let's get a sense for, first of all, what that eigenspace would look like, and second of all, how we can associate that eigenspace with the eigenvalue lambda equals 2. So let's do the geometry first, and then we'll look at the algebra for how to actually answer these questions. For the geometry piece, what I'm going to do is use this Eigenfinder applet that I'm going to ask you to use a little bit more today, and just hunt around, because what it's showing us is it's showing us the purple vectors, which are our x's, and the green vectors are a times that x. So, for example, if I take the vector 1, 0 as my x, then the image of 1, 0 is this green vector, which happens to be 4, -2. So we're seeing both x and a times x on the same set of axes. So can we find a vector which a is doubling its length? Sure. How about this one? Let me try and make it as close to coordinate direction as I can here. So it certainly looks like this purple vector, when we multiply it by a, is just being stretched by a factor of 2. It's just being doubled. Its image is parallel to itself. That's how we can recognize it as being an eigenvector. But it's not the only eigenvector for lambda equals 2, because if I move it northeasterly, like this, that this vector is also an eigenvector with lambda equals 2. It's also getting doubled by multiplication by a. So is this one, and so is this one. It's also true down here in the third quadrant, that that vector is also getting doubled when we multiply it by a. And so is this one, and so is that one, and so on and so on. So these eigenvectors don't exist in isolation. They exist in entire spaces, right? And that is what we would call the eigenspace associated with that particular eigenvalue. That's weird. It's not cooperating in highlighting the whole thing, but let me just do this by hand. So the eigenspace associated with the eigenvalue 2 refers then to the entire set of vectors that lie along this line. So because it's an entire vector space, if I want to understand that space or describe it to someone else, the easiest way to do that is to come up with a basis for it. Eigenspace for lambda equals 2 is that entire subspace, entire vector subspace of the xy plane. So if I wanted to find a basis for it, I just need to find a spanning set, a linearly independent spanning set of vectors inside of that. By the way, what does it look like is the dimension of this eigenspace? How many vectors will I need in a basis to describe the entirety of that eigenspace? Like object. This eigenspace is just a line through the origin, and so this eigenspace is one-dimensional. Since we like terminology so much, this is a good time to mention that the dimension of an eigenspace also has a terminology associated with it. It's called the geometric multiplicity of that eigenvalue. Multiplicity. Ran out of room. So the eigenvalue lambda equals 2 evidently has geometric multiplicity 1 because its eigenspace is a line, a one-dimensional subspace passing through the origin. Okay, but now we want to find a basis for it. So it's going to require us to solve, if we want to determine a basis, we need to solve the eigenvalue eigenvector equation. A times v, or x, or whatever we want to call it, let's call it x, is equal to 2 times x, where 2 here is playing the role of my eigenvalue. So I want to solve this equation, but our tools of linear algebra are not sufficiently advanced at this point to deal with an x being on both sides of this equation. So before we can solve it, what do we have to do to it? Yeah, let's subtract so that we can get that 2x on the same side as the ax. So if I subtracted it from both sides of my equation, now my right-hand side is going to be the 0 vector. So we're making some progress because the x's are at least now all on the same side. But now I want to factor that x out, if we can. In other words, I want to see this as a single matrix vector equation where I have some matrix multiplied by x is equal to 0. But if I factor out the x, what I get looks something like this, a minus 2. But that's kind of silly, right? We don't exactly know what to make of that expression at this point, because how do you subtract 2, which is a scalar, from a matrix? In fact, what I'm really looking for here is I need to put, in place of 2 here, I need to put a matrix which has the same effect on the vector x as multiplying that vector by 2. What matrix can I put in between 2 and x to leave the value of that expression the same? The identity matrix. So that's what I'll do, is when I factor out that x, the cofactor in the parentheses there is A, our original matrix, minus 2 times the identity. And now we've turned the eigenvalue eigenvector equation into a matrix vector equation, the type of which we know how to solve based on the first half of our course. So we just need to figure out which vectors x satisfy this equation. And those x's are going to belong to the eigenspace of lambda equals 2. Lambda equals 2 eigenspace. So let's set up this matrix vector equation so that we can solve it. So what I need to do is take A, which is 4, negative 2, negative 2, 4. There's A. And I'm going to subtract from it twice the identity matrix. Well, what's the identity matrix? In the 2 by 2 case, it's just 1, 0, 0, 1. So I want to subtract 2 times as much. So really, I'm subtracting 2, 0, 0, 2. So subtracting twice the identity matrix from A is going to take this 4 up there and subtract 2 from it, so that it becomes 2. Then it's going to take this 4 down here and subtract 2 from it, so it becomes 2. And so at the end of all of that manipulation, this matrix, A minus 2i, is that matrix right there. 2, negative 2, negative 2, 2. So that's the matrix that this matrix vector equation is predicated on now. So if I'm to solve this matrix vector equation, the matrix I have on the left-hand side is going to be 2, minus 2, minus 2, 2. And then on my right-hand side, what do I have? I have the 0 vector. So notice, by the way, that when we turn the eigenvalue eigenvector equation into a matrix vector equation, the resulting matrix vector equation is actually homogeneous, always. The right-hand side of this matrix vector equation is always 0, which is good because that means that this is always going to be consistent. Homogeneous matrix equations are always consistent. But let's row reduce this matrix and find out what are the nature of the solutions of this system. Now that we know that it's always consistent, we want to know if the solutions are unique or not. So what one step can row reduce this matrix so that we can determine where the pivots belong? What do you want to do with these rows?
Add row 1 and row 2.
Let's add row 1 and row 2, because we're setting up this upper right-hand entry to be a pivot. Adding row 1 to row 2 will have the effect of clearing out this entry underneath. Negative 2 plus 2 becomes 0. Then adding this 2 to negative 2 makes that, also 0. And adding the 0 to the 0 above it gives us a 0. So again, we knew that this was going to be a consistent homogeneous equation. But now what do we also know about the nature of the solutions? Are they unique or are they not unique? The solutions are not unique, which, by the way, is what we expected to happen. We expect there to be infinitely many solutions because there were infinitely many vectors, eigenvectors if you like, that belong to this eigenspace. They don't come in isolation. We're not going to get a unique eigenvector. We're going to get a whole vector subspace worth of them. So that's what we expected to happen. We expected the solutions not to be unique. And again, they're not unique because this column, the second column, is missing a pivot. So we're going to end up with a free variable no matter how hard we try. But that's good. That's what we want when we're trying to find eigenvectors.
So there's an infinity amount of eigenvalues or
That's a great question.
vectors?
So there is an infinite number of eigenvectors because those are the infinitely many solutions to this homogeneous equation. But there are not, in general, infinitely many eigenvalues for a matrix. That's a question that when we talk about characteristic polynomials in the second section, that's an answer to that question. How many eigenvalues might a matrix have? It depends on its size. It depends on the dimension of the matrix, but it is always finite for a finite dimensional matrix. Let's finish this example by finding a basis for that eigenspace, which is equivalent to finding a basis for the solution set of this equation. Where is that going to come from? What do we have to do to find a basis for the solution set of a linear system of equations? By the way, since we're talking about a homogeneous equation, this eigenspace is exactly the same thing as the null space.
Since it was set equal to 0.
Right, because it was set equal to 0, because it was the homogeneous equation, this eigenspace is really the null space, but it's not the null space of A, it's the null space of the matrix A minus 2 times the identity. So in that sense, finding an eigenspace questions are equivalent to null space questions. So I can find a basis for the eigenspace by finding a basis for the null space of A minus 2i. And how did we do that? We just wrote our solution set in parametric vector form. 2x1 minus 2x2 is equal to 0. But then x2, what was x2 in this example?
Free variable.
Is free variable. So to get our parametric vector form, we'll just solve for our bound variable x1, adding 2x2 to the other side and then dividing by 2. We find out x1 is equal to x2, and x2 is free. So we're just going to give it a meaningless parameter name, and x1 will inherit that name as well. So package these into a vector, and what does my solution set look like? T times what?
1.
1. If I factor the t out of this vector over here, that's what I get. So what is a basis for my solution set? It's the vector 1, 1. And because it's a solution set of the homogeneous equation for a minus 2i, it's a basis for the null space of a minus 2i, and is therefore a basis for the eigenspace of lambda equals 2. It also happens to agree with our picture. After all, what's the vector 1, 1 look like? It's that vector right there that lies along the line y equals x, which was exactly the line that we were talking about that determined our eigenspace for lambda equals 2. So if we happen already to know the eigenvalue that we're looking for, we can find, and this is the tricky step it turns out, we can find a basis for the eigenspace just by finding a basis for the null space of a minus that eigenvalue times identity. And to find that basis for the null space, we just set up its homogeneous equation and determine its solution set in parametric vector form.